Welcome to the heart of statistical inference. In every scientific study, from medical trials to economic forecasting, we face a fundamental question. Is the effect we see real, or is it just a random fluke? To answer this, statisticians use hypothesis testing, a structured framework to make decisions under uncertainty. Today, we will explore the two primary paths to reaching a conclusion: the critical value approach and the p-value approach. Both lead to the same destination, but they offer different perspectives on the weight of evidence. To start, we must define our ground rules. In any test, we have the null hypothesis, H0, usually representing no effect, and the alternative hypothesis, HA, representing what we aim to prove. Before looking at the data, we choose a significance level, denoted as alpha. Typically set at 0.05, alpha is our threshold for risk, the 5% chance we are willing to accept of being wrong when we say an effect exists. This choice defines our rejection region on the probability distribution. The first road is the critical value approach. Imagine a standard normal distribution, the familiar bell curve. Based on our chosen alpha, we find a specific point on the horizontal axis called the critical value. This value acts as a physical boundary. If our calculated test statistic, such as a z-score or t-score, falls beyond this boundary into the tail of the distribution, we reject the null hypothesis. It is a yes or no binary system favored in quality control and classical engineering. The second road is the p-value approach, the probability path. Instead of looking for a boundary, we look at our data and ask, if the null hypothesis were true, how likely is it that we would see a result this extreme? The p-value is the area under the curve beyond our observed statistic. Unlike the fixed boundary of the critical value, the p-value provides a continuous measure of evidence. The smaller the p-value, the stronger the evidence against the null hypothesis. How do these two roads meet? It's a matter of comparison. In the critical value world, we compare a score to a score. Is our z-statistic greater than the z-critical? In the p-value world, we compare a probability to a probability. Is our p-value less than alpha? Mathematically, if your test statistic is further out than the critical value, your p-value will automatically be smaller than alpha. Both methods will always yield the same decision, either reject H0 or fail to reject H0. In modern science, the p-value has become the standard because it tells us not just if we pass the threshold, but by how much. A p-value of 0.001 is much more convincing than 0.049, even though both lead to a rejection of the null at the 0.05 level. However, beware of p-hacking, the misuse of statistics to find patterns where none exist. Statistical significance does not always mean practical importance. A result can be mathematically significant, but useless in the real world. To conclude, whether you choose the rigid boundary of the critical value or the fluid probability of the p-value, you are performing the same logical operation. You are testing the strength of your signal against the background noise of chance. Understanding both roads ensures you can interpret data with the rigor and nuance required in the professional world of analytics.